we are going to finish doing a little more review and then start in on chemistry. So hopefully yesterday's lab experience got you a little more familiar with electric charge and what we're going to have there, as well as you all got to appreciate what it's like to get a little shock, and see your hair stand up a little bit. Whose hair stood up the best? Danny's?
Mine did really well when you guys left.
Yeah, I know. Yours didn't stand up, Mariah, because you weren't here for lab yesterday.
Yeah, I know. I went to work. I'm sorry.
Okay, reviewing the last couple chapters. Chapter 7 and 8, I think we're talking about thermodynamics, or was it 6 and 7? Anyway, we talked about thermodynamics, and we have three mechanisms for heating. We have the mechanism of direct contact, which is conduction. I'll change the color. We have convection. How is convection? What is the mechanism for heating through convection? What? Okay. Convection is when you have some intermediary fluid. Remember, I held my hand above the flame, and the hot air, because it's hot, means the kinetic energy is higher. Molecules hitting off each other expand. They're less dense. Because they're less dense, they float upward. And so you have a natural convection. You have a natural upward flow of the hot air. So you put your hand above and it gets hot, whereas you put it at the side, it's not so bad. Well, that's what was occurring there. You can have forced convection, like a convection oven is forced convection, where you have a fan that blows it. So it goes whatever direction the fan blows it. Or we talked about weather patterns and how you have air over land will heat up during the day, and because it's hot, it expands and rises, and cool air from the ocean will flow in underneath, and then at night it reverses. So there's lots of things that can cause convection. So the key to convection is it's a flow through a fluid. Even in the ocean, there's convection currents in the ocean that take cold Arctic water all the way down around South America up to the Atlantic, and then back around South America and up to the Arctic. It's this big cycle, a convection cycle, with water being the fluid that's carrying the heat. Okay, so that was a fluid intermediary. I'm just going to put that word. Intermediary is not spelled that way, though. And then the last mechanism was radiation. That's electromagnetic. E.g., light. Light is an example of an electromagnetic wave. Now, we didn't study light because of time. In the waves, we only talked about waves in general. But light is a type of wave. And so when you stand in sunlight, you're being heated up by the sun. Newton's law of cooling, remember I talked about like CSI, they stick the old thermometer in the liver to measure the liver temperature, because the rate at which something cools is proportional to the temperature difference between the environment and the object. That's Newton's law of cooling. So if you have a body that's at 98.6 degrees Fahrenheit in an environment that's at, let's say, if you were to die right now, 20 degrees Fahrenheit, then the rate at which you cool is proportional to that temperature difference. And as you are cooling, the rate is going to slow down, but they can then track what's your temperature now, what's the outside temperature been, and they can calculate how long it's been since your temperature was 98.6, and thus how long it's been since you've died. And then finally, understand how the greenhouse effect works. It's something that's been big in the news for the last probably 20 years. And so it's important to understand this greenhouse effect. What would happen on Earth if there was no greenhouse effect? there wouldn't be life because we'd be popsicles. We'd all be frozen. That's one of your homework questions. What would happen on Earth if the greenhouse effect was too great? There'd still be no life. We'd all be crispy critters. So we have to have something in between for the greenhouse effect for us to survive. So it's important for survival, but if it's too much, not good. Too little, not good. Okay, chapter 8 was static electricity and current. So chapter 8, electricity. Electricity, you studied it in lab yesterday. You need to know what electric charge is. What are the two things that fundamentally have electric charge that we deal with? Electrons is one of them, that's right. And what's the other one? Protons. Protons have a positive 1.602 times 10 to the minus 19 Coulomb charge. Electrons have a negative 1.602 times 10 to the minus 19 coulombs. It'll be on the actual value of the charge. Yeah, probably be on the equation sheet. But you definitely need to know electrons have a negative charge, protons have a positive charge, and the magnitude is the same. You have to know those things. Question?
I have 1.6. Is that okay?
Yeah. I'm just putting more decimal places. So 1.6 is fine. So they have the same magnitude charge, but electrons are negative, protons are positive. And all of the charge things we deal with are because of that. So we had the example of an amber rod rubbed on fur, or as we did in lab yesterday, rubber balloon rubbed on hair, and you have charge transfer. So that you end up with the hair has a positive charge. If it has a positive charge, what happens to the hair? It was initially neutral, had no charge. If it became positive, what had to happen? Okay, because our charges are either protons or electrons, there are two answers you could give, but only one's correct. To be positive, it either have to gain protons or lose electrons. But it lost electrons because the protons are fixed. The protons don't move around. It's only the electrons. So your hair lost electrons. Where'd those electrons go? Onto the balloon. So the balloon had extra electrons, hence it had negative charge. Your hair had missing electrons, a positive charge. And then there's an attraction between your hair and the balloon because opposites attract. But when you took the two balloons and you brought them close together, they should have pushed apart because likes repel. And then we had that funny electric polarization. Water is an electric dipole. Water molecules, you have an oxygen that has a charge of minus 0.70 E, where E is this value here. And then you have the two protons, the two hydrogens, I should say, each one with a charge of plus 0.35 E. So the water behaves as if it has one part is positively charged, one part that's negatively charged. We call that a dipole. And if I bring some random positive charge here, what's the force going to be like between the hydrogen and that positive charge? Positive and positive. They repel. So there's going to be a force that pushes the hydrogen away. What about the force between the oxygen and that positive? It's going to attract. So there's a force that attracts the oxygen. So the whole thing is going to reorient. I don't think I can rotate, so I'm not going to. Well, let's see if it does. It's pretty amazing now that it's working again. Yeah, there's no rotation option here. Oh well. So it's going to rotate so that you're going to have the molecule like this. Here's the oxygen, the hydrogen, and the hydrogen. And now you have the negative closer and the positives farther. It's an inverse square law, the Coulomb's law. That means that the force is proportional to 1 over the separation squared. Because the oxygen is closer, that's going to be the stronger force. And so the attractive force will be stronger and it gets pulled in. Where did you see that in lab yesterday?
No, not the little bubbles.
The little bubbles. When you blew the bubbles, those tiny bubbles went zoop and were pulled into the Van de Graaff generator. Why were they pulled in? Because the water molecules are orienting and then being attracted. But sometimes they got pushed away. How'd that happen?
Because it was too close and so it's just a hydrogen.
Not that it was. It has to do with proximity, but it's not that aspect. If the water molecule, or if the bubbles get some charge on them, they're going to get some charge because there's excess charge on that Van de Graaff generator. And so if the Van de Graaff generator, let's say the Van de Graaff generator is negative. So it's spraying off electrons. And so if you collect a few electrons on that bubble, now it has the same charge as the Van de Graaff generator, and then you have a repulsive force that's going to be stronger than this dipole force. And so once they transfer charge, then they were pushed away. Obviously, yesterday's lab was totally cool in preparing you for the test. Or I hope so. That was the plan, at the very least. Final chapter for review is talking about vibrations. We talked about vibrations versus waves. What is the difference in a vibration and a wave? Has to do with motion.
Vibration is a wiggle in time.
Okay, vibration is a wiggle in time, and a wave is?
The distance to repeat that it repeats.
Well, that's called the wavelength.
So the travel.
It travels. A wave is a traveling vibration. The book says a wiggle in space instead of a wiggle in time, but it's a traveling vibration. So you need to know the difference. And then we had transverse versus longitudinal waves. Remember, I was out there with my, Leslie helped me, and I had the spring, and we demonstrated waves where the particles were moving vertically, but the wave was traveling horizontally. And when you have the direction of motion perpendicular to the direction that the particles, or that the wave is traveling, direction of motion for the particle is perpendicular to the direction the wave is traveling, then that's a transverse wave. On the other hand, we did a wave where the particles were moving back and forth horizontally and the wave was traveling horizontal. That is a longitudinal wave. Question?
What did you say vibration was again?
Vibration was something oscillating in time. So make sure you know the difference between a transverse and a longitudinal wave. And some examples, a sound wave. Which kind of wave was a sound wave? Longitudinal. Light waves are electromagnetic. They're transverse waves. So those are common examples of the two. If you look at a water wave, if you pay careful attention to a water wave, how many people have enjoyed playing in the surf with waves coming at you? I actually have to ask this here. You know, when I was in California, everybody did. You know, we've got the beach. But here in Nebraska, there is no beach. Anyway, in the water, if a wave is coming toward you, what direction do you move? If your feet are up and you're floating, the wave's coming toward you, what direction you move? It pulls you toward the wave. If you have the wave is coming like this, and you're here in the water, it pulls you that way. But then when the wave comes, what happens to your motion? You go up and then you go forward. And so your actual motion is kind of in a circle. Would that be a longitudinal or a transverse wave? It's a trick question. It has both aspects, right? Because you had motion that was parallel and motion that's perpendicular. And so that's a combination of a transverse wave and a longitudinal wave. So water waves are combinations. So are earthquake waves. In earthquakes, we often talk about the P wave and the S wave. Those are waves that go through the bulk of the earth. The P wave is a longitudinal wave and the S wave is a transverse wave. P stands for primary or pressure. It's the faster one and it's the longitudinal one. S stands for secondary or shear. It's the transverse and it's the slower one. So the bulk waves going through the earth, two different types. We'll talk about this when we get to geology. You also have surface waves. How many people have been in an earthquake that was big enough to feel? Once again, I have to ask this. In California, I don't have to ask. Everybody's like, duh, 2 months ago, don't you remember? If you're on the surface, you have, once again, combination waves. You have waves that are called love waves or Rayleigh waves that are combinations of transverse and longitudinal waves. So some earthquakes, you'll feel a lot of up and down. Some you'll feel a lot of forward and backward, and some you'll feel rolling because you have the different waves combining on the surface. Okay, with the waves, make sure that you can identify the frequency. That's the number of cycles per second. Standard unit there is hertz. 1 hertz is 1 cycle per second. The period, which is the time per cycle. And the relationship between period and frequency is very simple. Period is 1 over the frequency.
So frequency is the cycles per second?
Frequency is cycles per second. Period is time per cycle. Displacement, that's how far something is moved from its equilibrium position. Amplitude is the maximum displacement. So you have something that's moving back and forth, its displacement is changing. The amplitude is the maximum distance it got away from its equilibrium position. So that's, we'll consider a constant for this class. And then finally, wavelength that Ashton was defining. The wavelength is the distance for the wave to repeat. So the period was the time for the wave to repeat. The wavelength is the distance for the wave to repeat. And then finally, make sure you know the speed is equal to the wavelength times the frequency. You have a homework question that asks about this. Let me just tell you, that's kind of a trick question too. Make sure you read it carefully. The homework question that asks, it says, this friend says wave speed is frequency times wavelength. And this friend says it's wavelength divided by period. Which do you believe? Make sure you answer it carefully. Okay, that's the material that's going to be covered on the test. Now, obviously, I didn't tell you these are the questions. You can look through your potential test questions. If it's marked with a little red scribble in the corner, it's one of the ones that could be on the test. Look through your quizzes because, of course, all the questions that are on the quizzes are ones that could be on the test. And then there's ones that will come from the textbook as well. Half of the questions will come from you guys, half from the textbook. And then you have the one question on the scientific method. So you really have exposure to 50 per, well, this half plus the 8 points, somewhere around 60 to 65% of the questions you have exposure to already. Question? No. All right, and when's the test going to be? Next Friday, just making sure. All right, going into chemistry. Chapter 12 is the beginning of chemistry, and we start off with very much physics ideas. I can't remember what the word the textbook uses. It says physics is the fundamental science, and chemistry is something else that's very similar in meaning. Chemistry, originally, all of science was physics, right? It was just one big term. And then as things got more and more in-depth, people understood better and better, they started subdividing. So chemistry is an area that got split off into its own field because it's got so much wealth of information. Chemistry is studying the interactions between atoms and molecules that make up everything. So it's a very fundamental physics. So chemistry and physics has a very large overlap. And so you have classes like physical chemistry, which is looking specifically at areas of overlap. We look at thermodynamics in physical chemistry, and we look at quantum mechanics in physical chemistry, because quantum mechanics is the physics that underlies why we have the certain relationships between atoms and molecules. So what we're going to look at this chapter is first looking at what atoms are, what the elements are. I've already mentioned those just a little bit. The periodic table and how it's organized as per Mendeleev. And then just a few more things about atom structure. So this is very much physics still as we start chemistry. When we go on and we talk about different kinds of bonds, an S bond versus a sigma bond, S sigma, P pi, and a pi bond, then we'll be moving into something that generally physicists don't talk about that's more chemistry. So 465 BC, everybody probably knows. What does BC stand for? Before Christ. So 465 years before Christ was born, Democritus came up with the idea of the atom, that there is some fundamental smallest piece you can get if you cut stuff into smaller and smaller pieces. So, if you think about it, there was a lot of science that was well understood by the time Christ was born. In fact, understanding that the earth was a sphere, that was already understood well before Christ was born. I believe the radius of the earth was already known at the time Christ was born. So we always think about, the time of Christ was pretty primitive, but they were fairly knowledgeable. They didn't have a lot of the details we have today, but we have learned from them to move forward. So Democritus said that all matter consists of atoms that are indestructible. You cannot destroy them. And they're solid but invisible, because obviously we don't see individual atoms. And you have different kind of atoms that might be different in sizes and shapes. And this one's good. Solids are small pointy atoms, and liquids are large round atoms. Well, there's no sense to that, but that was part of what he believed. So long time ago, the idea that atoms exist, it's still on OneNote. You can always. Then we enter Aristotle, once again, far before the birth of Christ. By the way, sometimes you see BC and sometimes you'll see BCE. What does BCE mean? Before Common Era. What's the difference in BC and BCE? The difference is, if you say BCE, you don't have to invoke the name of Christ. And so people who don't want to invoke the name of Christ came up with this idea: let's change what we call it. Instead of BC, let's call it BCE. And it'll stand for something different. And then if you're talking about AD, what does AD stand for? It's Latin. It's Anno Domini, the year of our Lord. Right, so this is in the year of our Lord, 2018. That means it would be, or 2018, yeah. So this would be the 2018th year of Christ, after Christ was born. If, of course, the calculation of when Christ was born was done correctly. The person who came up with this, it was, I think, around 530 some years after Christ, was off by a couple years. So Christ's birth did not occur in 1 AD as it should have. But with the new numbering system or labeling, they'll call AD CE for Common Era. So when you see dates with CE, that means Anno Domini, in the year of our Lord. They just didn't want to have to refer to Christ again, right? And BCE is before Christ still. So Aristotle knows he did not believe in the atomic theory. He did not accept Democritus. He said there are only 4 elements. Those 4 elements were earth, water, air, and fire. I've talked about their natural positions. That's what Aristotle believed. And people largely abandoned Democritus and believed what Aristotle said because you know what? He was really wicked smart. And people were like, if he's so smart, he's got to be right. Democritus was closer to right than Aristotle, but people used the logical fallacy of appealing to an authority. He is an authority, so he must be right. That's a logical fallacy. That's like saying the scientific consensus is that, what's something that used to be scientific consensus but is no longer? For some reason, the scientific consensus is that light is a wave. So it must be a wave. That was disproven in 1905. And so now scientists have to have a different thing. The whole appeal to authority that was used then, you have to abandon it. So it is important to realize that just because a scientist says it's so doesn't mean it's so. Just because your teacher says it's so doesn't mean it's so. There has to be some logic and reasoning for you to actually accept, that's the way it is. That's why we do the labs. I am not here to indoctrinate you. I'm not here to say, you will believe this because that's what science says and science is correct. I'm here to hopefully open your mind to seeing, wow, that's what happens, because it didn't seem like that's what happens. But now that I play around with it, I can see, that's what's going on. All that said, what are we going to see in chemistry? Well, we're not going to see the individual atoms. What we can see is behaviors, and so we'll do some labs where we try to learn about those behaviors. Get to 1880. Notice 335 BC to 1880 AD. We had John Dalton who explained why chemical reactions use exact ratios, like this much oxygen and this much hydrogen. If I put extra hydrogen, it's still only going to use this proportion of how much oxygen I have. So I can have an excess of 1 and it'll always be the right ratio. And so he said there must be something going on here. We must have atoms of different types and fixed ratios for the number of atoms that make up some molecule. And now it's time to introduce some words. So an atom is equal to a nucleus. That's not how you spell nucleus, by the way. Boy, I've gone completely nuts. I think that's it. Nucleus with protons and neutrons plus electrons orbiting the nucleus. So that's an atom. Elements are different types of atoms. So an element is made of only one type of atom. So each different type of atom, that's an element. You can talk about the different types of atoms or elements. So that table that's behind you is called the periodic table of the elements. And each box has a symbol for the element. So for instance, right in the center, we have RH, 45, rhodium. Now RH, the 45 up in the right-hand corner is super important. Actually, it's 46. I can't tell. No, it's 45. That's right. I could wear glasses, but I found them. Anyway, they put it in the jacket for a couple of years. The rhodium, that 45, is super important. That 45 tells you how many protons are in the nucleus. An element is defined by the number of protons in the nucleus. So any atom that has 45 protons in the nucleus is always rhodium. Doesn't matter how many neutrons are in the nucleus. Doesn't matter how many electrons are orbiting the nucleus. If it has 45 protons, it's rhodium. If it has one proton, what's it going to be? One person's looking at the table. Hydrogen, right? Because hydrogen is the one that has one up there in the core. That means it has one proton. So now for everybody, let's say it has 8 protons. What element has 8 protons? Oxygen, right. So you can see there's something important there. That number is what tells you what the element is. And so if I have an elemental form of something, that means I have something that's all the same element in it. So we have the element versus the atom. Pure gold has only one type of element, gold. How many protons are in gold? This is a trick question. What's the symbol for gold? AU, that's right. So how many protons are in gold? 70, how many? 79, because there's no chance I would be able to read it from here. So it has 79 protons. We usually write that 79 right there. Now it also has a lot of neutrons. Now you can have more than one isotope of gold. Isotopes have the same number of protons, but different numbers of neutrons. So you could have a gold atom that has, if you look in the gold, you have another number that's in the bottom center, which I can't read until I get pretty close. In the bottom center it says 196.967. Between you and me, we'll call that 197. That means that the average number of protons plus neutrons in gold is 197. But you could have a gold atom that has an extra neutron, 198. That's a different isotope of gold. But it's still gold because it has the right number of protons. Just has an extra neutron. So isotopes, same number of protons, but different number of neutrons. Here's an important thing to identify the isotope. You have the letter P. It has, iso is same. Let's not worry about the TO and E, the toe. Same number of protons. Iso is same, so it works out. I say that because there's another word. Isotone. If we ignore the toe, it's iso-N. What would N stand for? Okay, nucleus actually would make sense. I didn't think about that. It's neutrons. So it has same number of neutrons, but different number of protons. Now, we'll probably never talk about isotones, but just, throwing it out there. Now, we've already talked about the word ion. What does an ion mean? It has a charge. A neutral atom, if it's neutral, what's the relationship between the number of protons and the number of electrons? The number of protons and the number of electrons are the same in a neutral atom. An ion has a charge, so they're not the same. So if the number of protons is greater than the number of electrons, then it has more positive charge than the negative, and it has a net positive charge, then it's a positive ion. So if I take my gold that has 79 protons and I yank an electron away so it only has 78, then that's a positive ion. And we refer to that as gold with a +1 charge. +1 because it has one more proton than electron. And if we reverse this, if the number of protons is less than the number of electrons, then it's negative ion. Now there's some order in that periodic table. The periodic table, well, actually, let's go through the periodic table slides instead of me describing it now and then getting to the slides that I've already talked about that. In 1904, J.J. Thomson discovered that electrons are part of atoms. Now, we've just been talking about that, but it wasn't until 1904 that it was identified that electrons were part of atoms. When I was your age, I would have said, and that was in the 1970s. Well, no, when I was your age, it was the 1980s. Take that back. I would have said 1904 was ancient history. But now that I'm past 50, I'm like, that wasn't that long ago. I mean, my grandfather was 4 years old in 1904. He's long since dead. You guys, my grandmother died at 105. Anyway, I'm proud of that 105, so I had to mention it. So he came up with a new model of matter that's called the plum pudding model that I already described about a week and a half ago, I think. Was it a week and a half ago? Maybe it was last week. The plum pudding model that says that atom has a bunch of positive charges spread everywhere with little like raisins, because plum pudding is some kind of pudding that has raisins. And those raisins would be the negative charges. But then Ernest Rutherford, and actually it was an experiment that was done by Marsden, did an experiment where they found that you had to have a very massive core to the atoms, which didn't match at all with the Rutherford model, the plum pudding model, or not the Rutherford model, with the Thomson model, the plum pudding model. And so because he found that there had to be that massive core, he said it must be like a planetary system with a core that is very massive, and then the electrons going around like planets orbit a star. And so that was the model of Ernest Rutherford. Notice this is 1909. How many years? Only 5 years from Thomson's model to Rutherford's model. Well, then Niels Bohr comes over from Denmark. My family left Denmark only about 5 years before this. And he's working with Rutherford, and they realized right away that there's some real significant problems with Rutherford's model. And so Bohr comes up with what we call a quantum model of the atom. The quantum model of Bohr says that the electrons orbiting the nucleus can only have certain angular velocities. Basically, that's like saying, okay, you have a figure skater. The figure skater can rotate at this speed or can rotate at this speed, but can't rotate at anything in between. That's essentially what Bohr said. And it answered a lot of problems about the atom that Rutherford's model had. And so that was yet another model. It's called a quantum model because you have quantized values, only specific angular momenta, which resulted in only specific energies the electrons can have. So if you think about the planetary model with the planets orbiting the sun, the quantum model would say a planet can orbit this far from the sun or this far from the sun or this far from the sun, but it can't be anywhere between those places. And that's what Bohr's quantum model said. This quantum model also had some issues. And so we've gone forward to today's actual quantum model. Today's actual quantum model says that we have a whole lot of things that are quantized. The angular momentum is quantized, Bohr said it was, but the energy is separately quantized, and this is the weird one. The position for the electrons, we have no idea. We don't know where the electrons are in an atom. Now, we can do calculations about where the electrons are most likely to be found, but we can't tell you where they're going to be until you do some experiment. And so this picture on the right is the most accurate depiction we can make of an atom today. You have the nucleus. Now, the scale here is wrong. The size of the atom is like 1,000 times the size of the nucleus. So the nucleus would just be a dot if this was to scale. So you just have a dot in the center, and then you'd have this big fuzzy cloud. And that fuzzy cloud is the volume within which you find the electrons. And we can calculate the probability of the electrons being at certain radii, certain locations, but that's all we can do. We can't tell you what path they're taking, so we can't say, oh, the electrons are doing circles because it's an s orbital. No, that's wrong. We can only say that they're most likely to be found in this the spherical shell that has thickness to it. It's most likely here, but it could be out here, it could be in here, if it's in an s orbital. And then we have other orbitals with different shapes. We have the p orbital, which looks kind of like a figure eight. And that figure eight is saying it's most probable to be in that volume defined by the figure eight if you were to rotate it about its symmetry axis. And then there's other orbitals. There's the d orbital, which gets more convoluted. I think that I took a d orbital for this one. And they go on. There's sp, d, f, g, and it goes on from there. So the electrons can have different energies. They can be in the lowest energy, called n equals 1. And so we have our orbital energy is defined by a quantum number, n. That n tells you primarily the energy. Not completely. The energy is also affected by the other quantum numbers, but it's primarily the n. And then we have L. L, it says here, tells you the orbital shape. It also tells you the angular momentum. So M also tells you the angular momentum. The two are combined to shape an angular momentum. M sub L, the M stands for magnetic. When you take atoms and you put them in a magnetic field, their energies will shift. And the M sub L is telling you about the shift in the magnetic field because of the angular momentum, which means it's telling you about the orientation of the orbit of the angular momentum. And then there's M sub S. Turns out electrons behave like little bar magnets themselves. We call that the spin. They're not spinning. The spin does not refer to spin. It's named spin because when it was conceptualized, that's what they thought was going on. But now we just say the electrons are like little bar magnets, and the M sub S is telling us how that little magnet is oriented. And so we have those 4 quantum numbers that give us the properties of an atom. So our periodic table back there is built on our understanding of these. First of our clicker questions. Had this going forever. Don't worry, we got 7 minutes left.
Can you put more than that?
Yeah. Put in the ones you believe to be correct and hit enter.
Incorrect? Oh. Wait. It says incorrect.
Yeah, yes, the ones you believe to be incorrect. I'm sorry.
What's perpetually again?
Perpetually, that means continuing forever. Like, husbands are perpetually wrong.
changed the channel, I just realized that. Gosh. 33?
Yes. Okay. So there's the answers we had. Which of the following are incorrect? 3 people said atoms are mostly empty space. 1 person said atoms are perpetually moving. And 4 people said atoms are manufactured in plants and in humans during pregnancy. Let's talk about each one of these individually. I've got a new set of cards because everybody's answered once. So first up is that person. Gabby, number 1. Speak about number 1. Atoms have been around since the beginning of the universe. Do you think that's a true or a false? And then your reason why.
I think it is true. Because everything is an atom.
Okay. Now I didn't talk about this directly. It probably was in my slides. But the atoms are, generally speaking, not created or destroyed. Molecules can be created or destroyed. I mean, our bodies work. The reason I can sit here and walk around is because molecules are being reconfigured in my body, releasing energy. But the individual atoms are just recycled. So we actually can do the calculation, it's not that hard, about the number of atoms in your lungs right now, in the air in your lungs right now, that were in Julius Caesar's last breath. And yes, statistically, each one of us has a few atoms in our lungs right now that were in Julius Caesar's last breath. The atoms are lasting forever, they're just recycled. Perfect answer. Okay, next up. Obviously, we're going to get through half the class today. Sam, atoms are mostly empty space. What do you think?
That was true.
Why do you say that?
Because it's just the nucleus, and then you said it was just like the dot, and then everything else was like the cloud of electrons.
That's our current understanding. We have that current, that's perfect, yes. We have that current understanding because of Rutherford's experiment, plus a lot after that showed that, and I talked about Rutherford's experiment more carefully actually, a week or so ago, that you had most of the alpha particles just went straight through without touching anything when they went through that gold foil. So that meant that the alpha particles mostly just went through empty space. But when they hit something, they did something crazy. That's what told them they had a nucleus that was very massive. So Rutherford's experiment is where we have the information that suggests that it's mostly empty space. Okay. Third up is this card. Mariah. Atoms are perpetually moving. Yay or nay?
Actually, never mind. I think they are because they have to continue to
Okay, to lead to the right answer, she's going the right way. To lead to the right answer, what is temperature a measurement of?
heat.
Not heat. Kinetic energy. Temperature is a measurement proportional to the average kinetic energy of the molecules. What does the third law of thermodynamics tell us about temperature?
The third one?
I told you that was the one that's kind of a...
Oh, nothing can be absolutely zero.
Yeah. Nothing can reach absolute zero, which means nothing can reach zero kinetic energy. So if your molecules can't reach zero kinetic energy, what does that tell you about their motion? They're always moving. They may slow down a lot when you get really, really cold, but they're always moving, so they're perpetually moving. Also, what I actually meant to write when I made this question was electrons. I put 2 T's there. Excellent. Electrons in atoms are perpetually moving. Also true. So now I get to the last one. Atoms are manufactured in plants and in humans during pregnancy. What do you think, Ivy?
That's incorrect.
That is incorrect. Why? Because what?
Because it's the last option. No, I don't know.
Okay.
I was confused about that one. I didn't understand.
It actually goes back to this one here. Atoms have been around since the beginning of the universe. The atoms aren't generally created or destroyed. There are some very special places where they are. Atoms are created when a star dies. Atoms are created actually in the cores of stars while they're burning. So the sun is right now converting hydrogen atoms into helium atoms. But those are special cases. Not in plants, not in humans. We're not creating atoms. We are modifying molecules, but the building blocks are the atoms. So the ones that were incorrect were this one here. And nope, just that one. All right, I'll see you on Monday. Have a great